Welcome to chapter 4, and I think the 9th video. We're going to enter into a whole new idea, whole new topic here, and that has to do with isomerism. We introduced some forms of isomerism already, and we're going to approach it in a much more interesting way, I think, right now, in that what we have in isomerism is a number of forms, and we saw a lot of constitutional isomers, meaning they've actually pulled the atoms apart and put them in different positions. We could have, one pentanol or two pentanol, or or we could have, cyclobutene or cyclobutane or butene. They're both C4H8, but they're different conformations, obviously. There's a number of different constitutional isomers, branch versus straight chain alkanes or constitutional isomers. We're going to look at conformational isomers. We've already seen one form, and that is cis-trans or EZ geometric isomers around a double bond. And of course, we'll come back to that as we get into like the lower left branch you see there in front of you, where things are locked in place. What I'm going to talk about now is important that you understand, but it's a little more elusive. That is, we're going to talk about conformational isomers that freely rotate. So what do I mean? What I mean is, let's say you have ethane. Pretend the blue ones are white, they're hydrogen. So this is C2H6, and this molecule freely rotates. Is there, and of course, when it does, it changes conformation. Strictly speaking, those two hydrogens, not those two hydrogens. And certainly, if I turn it like this, so that it's like this, I wish I could do a better job of this, that would be a different molecule than if it was that, where they were all lined up, right? So we're going to look at these freely rotating sp3 conformational isomers. Now, assuming this is ethane, how much hindrance is there on free rotation? And the answer is not very much at all. However, there is some. If you think about it, these are electrons, and these are electrons, and these are electrons, and those are electrons. And back here, those are electrons, two electrons in a covalent bond. And it's intuitive that as two hydrogens, let's line it up here, come past each other, they would repel. So that as they were trying to come towards each other along this CC bond, they would actually repel and then fire each other off as they repelled and started to speed up and then slow down. I don't know if they speed up or slow down. It's kind of not the point. But they would repel and then not repel. And so there is a small amount of hindrance on free rotation, not enough that ethane is ever hindered in turning. The ambient temperature of this room is way more energy than you need, which is about 2.9 kilojoules. We'll see this graphically. What I want you to know is that this molecule basically has two conformations. It has where they're as far apart as possible. When they're as far apart as possible, we call them staggered. And so here's the staggered conformation of ethane. You'll notice one straight up, one straight down. The straight down one's in front of you, the straight up one's back here. You can see it back there, right? And so there's the staggered conformation. The other way that they could interact is this higher energy form in which you'll notice it happens 3 times, bottom left, bottom right, top, where it actually has the strain of the electrons repelling each other. And this is called the eclipsed form. So staggered, eclipsed, staggered, eclipsed. This is actually famously referred, for obvious reasons, to as when it's eclipsed as the sawhorse conformation. See, it's like, well, sawhorses used to be a thing when people did woodworking, but a sawhorse. But what I really need you to know is eclipsed, staggered, eclipsed, staggered. And we have to give a name to the strain, and it has to do with the rotation and the strain inside these electrons. And it has to do with twisting and turning around those bonds. So it's become known as torsional strain. So the torsional strain is in this space in between. Doesn't have to do with the hydrogens, has to do with the electrons. And it's not a huge amount of force. Although in some, 2.9 kilojoules here and 2.9 down here and 2.9, it plays a role. And so what we see is that, let's say we call this, and by the way, let's describe these angles along the length of this CC bond as dihedral angles. And let's say that what we have is an opportunity to go all the way around, right? So all the way around is 360. So that's 180. There's 180, right? Versus them, the blue ones, which are also hydrogens, but I've made them blue for examples. There is 180. So if that's true, then it's 0. Staggered is 60. 120. 180. And so on. So we have staggered and eclipsed in ethane. We have dihedral angles that go through 360, although it's we sort of think of it as 60 degrees or negative 60 degrees, right? But anyway, so, and not a huge amount of energy consumed by this. If we look at that PowerPoint, so here's the idea of staggered and eclipsed through that dihedral angle, looking down the end. And what we see is staggered eclipse, staggered eclipse, staggered eclipse. And logically, or it's 2.9 kilocalories, 12 kilojoules, I apologize. What we see is that eclipse, the torsional strain, causes it to be of higher energy, and when it's staggered, it goes to lower, and it just like a sine wave from staggered to eclipse, due to the torsional strain. This brings up a notation method that I want you to know. And this notation method is called Newman projections. Newman projections take this, I'm going to draw it like this. Here's an eclipsing conformation. And it says, let's look at it, write down that CC bond as I've been doing, right? So there you go. There's the eclipsing version of what I just drew, looking down the two carbons. So let's draw the front carbon, right? So we're looking, let's say we're looking, that's supposed to be my eye. We're looking in that direction. And there's the front carbon. So how do we show this back carbon? We show it as a circle. It's an assumed carbon back there. And it's, well, we're going to show it as eclipsed, not staggered. So when it's eclipsed, put all the hydrogens on the same side, just so that it looks right. So there is an eclipsed. And this is a freely rotating conformational view of ethane. Now, it seems intuitive to me that there's a whole new thing going on when these are not hydrogens. Let's say they're methanes. They're actually big, bulky groups. They consume space. And that requires us to know a new vocab word. And that vocab word is sterics. Sterics is simply about size and bulk and conformational inhibition or favorability, not due to the nature of the carbons, not due to the charge of the carbons, but due to the bulk of the atoms involved. Let's say this is butane. So here I have butane. This blue ball no longer does it justice because it's a CH3, right? It's a big molecule, right? And when that is true, when this is butane, look, if this is butane, here is trans, the E conformation, and here is cis. Cis is the C, is the Z conformation, right? So now we have a whole new thing going on, because now when you have butane, CH3, CH2, CH2, CH3, we have a whole new conformational issue in that this staggered conformation or eclipsing conformation wouldn't be the same as this eclipsing conformation, because when these two come by each other, they might actually, the hydrogens you could picture them branching towards each other, like actually smash into each other, they would hate it. So not only do you have torsional strain here and torsional strain here, but now you have strain due not only to the torsional, which exists, but due to that bulk, which logically is called steric strain. So in this case, we have a whole new thing going on. Let's put those as far apart as possible. So it's a staggered conformation at 180 degrees. Logically, I think logically, that's the lowest energy conformation you can have. These two guys are as far apart as possible. And not only that, you've eliminated steric strain, and you've minimized the torsional strain by being in a staggered conformation. Now, let's say I start to rotate these towards each other. Well, I'm going to create not only 3 torsional strains, but now I'm going to create a little bit of steric strain with that methyl and that hydrogen, a little bit of steric strain, methyl and hydrogen. So in other words, this conformation, this eclipsing conformation, is higher in energy than it would have been if it was ethane, because now I've added in this new strain. And then I go towards these two. Now, here's a problem. When I get to 60 degrees, which this is supposed to be, when I get to 60 degrees, roughly speaking, when I get to 60 degrees, now I've got not just, well, I've got it in the staggered conformation, which is lower in energy, but make no mistake, these two methyl groups are aware of each other. These are repelling already because they're both big and bulky, sterics. So this is not going to be as good as the 180. So 60 and 180 are not the same energy. And as you can imagine, this is the worst. If you have the eclipsing conformation with both bulky groups right on top of each other, you've got 3 torsional strains and a massive amounts of steric strain right there. So we have some vocabulary so that we can easily identify and describe these. So what I have here is the lowest energy conformation. And because they're opposites of each other, we call this the anti-conformation. So you go from anti, which is lowest in energy, to eclipsing, but not as bad as it could be, to staggered, but now the staggered is not very good. The atoms are now, these bulky groups are now coming towards each other. When they are staggered, but 60 degrees apart, it's not the anti-conformation. It's not very nice. And the French word for that, as you know, actually the French word for left, which is interesting, is gauche. And this is a gauche conformation. It's not very nice. And then this is the worst. This is the eclipsed steric and torsional strain. So let's look at that graphically. So now we have a whole new thing. I know it says 1,2-dibromoethane. These could have been bromines, and it would be the same idea as butane. So what's the lowest conformation energy-wise? Well, it's on either end, right? So at the minus 180 or 180, at 180, it is anti, and that's the best. It's the lowest energy, right? There it is, more or less, right? The anti-conformation. Notice the Newman projection has 1 bromine up in front. I should have done it like the image. 1 bromine up in front, 1 bromine back in the back in my hand. Then as they come towards each other, you first encounter an eclipsing conformation. Eclipsed is bad, right? And not only that, but you can see that it's not 12 kilojoules because of these bromines, these sterically bulky groups. You've got steric strain going on, so it's up above, 25. It's at 25. And not only that, when you get to these gauche conformations, you would think they would be pretty good because they're staggered, but look how much worse they are, that staggered conformation, than the anti-conformation. These gauche conformations are not good at all at 60 or minus 60, right? 60 and minus 60, they mean the same thing. So, and then of course, energetically, an eclipsing conformation with the steric strain going on. Oh, it's terrible. And while 40 kilojoules is, energetically unfavorable, it's still able to freely rotate, right? But remembering butane, imagining these to be CH3s, this is the most favorable conformation. And this is the one it tends to. Does it freely rotate? Sure. But it would, ethane would, or butane would rotate through there and come back to here and rotate through there. Even the room's temperature provides enough energy for it to rotate. Where does it find lowest energy? There. And because of that, when we draw long hydrocarbons, octane, we draw it as a zigzag, right? And first of all, obviously, if we drew it as, any other shape, it would be messy. But this is actually, this zigzag, this, 180 anti-conformation is the lowest energy state. So zigzags actually represent the tetrahedral reality of something like octane. So these are for you. It's the image we've been talking about and the Newman projections that you have to be able to draw. And you have to be able to identify without the words below them, which one is gauche, which one is anti, right? 60 degrees in either positive or negative direction is gauche. 180 up and down is anti. And of course, none of those are as bad as eclipsing conformation. So the same image again, just found for you. In either end, you have 180, the anti-conformation. It goes through eclipsing, but not hysterically as strained as it could be. It falls to gauche, which is 60 in either positive or negative direction. Gauche is bad. Gauche staggered is much worse than anti-staggered. And then you go to the eclipsing butane, that cis sort of conformation, and you see how much energy is required there. And then we talk about how that's a zigzag conformation. All right, so I'm going to stop here and we'll pick up with angle strain in the 10th video. Thanks for watching. I know these are, time consuming and they're trying mentally, but hopefully with repeat watching, you'll find that they're really valuable. And I welcome suggestions and ideas. All right, see you in video 10.